Hello?
Hello.
Hi.
Hi. Yeah. You have joined?
Oh, good, thank you. How are you?
Yeah, I'm fine. Fine. So let's join the class, right?
Yes.
Okay. So let me share the file, right?
Yes.
Last. Okay. Um, yeah. Can you see the screen?
Yes.
Okay. So what this is about? This is the literature review that you have shared.
Yes.
Yeah. This tells about the bug boost. Like you want me to explain, right? This thing.
Yes. What I want you to do is read everything with me. If there is something like complicated, you can explain it.
Okay.
And we'll see where we will finish. Maybe we will finish it today, maybe not. That's fine. We can take another class if we don't finish it. But I
Okay.
want everything to be explained so I can explain it to the professor.
Professor. Yeah. So you want like whatever is there, like basically you want to want me to explain, right?
Yes.
Okay. No problem. See. Okay. So in this case, it's telling about first it started as the bug boost converter since our uh, project mainly involves the bug boost converter. Okay.
Yes.
So it tells that a buck boost converter is a what? It's a DC-DC converter, right?
Yes.
DC-DC means direct current to direct current.
Yes.
Okay. Which mainly operates in two mode, buck mode and boost mode.
Yes.
I told you in the last class that there are two modes of buck boost. So have you checked? Have you checked?
Yes, for the back mode, step down, and the boost mode, step up. And you explained how it can step down and step up the voltage and the current.
Yeah, but I also told you that you asked me a question like when it will be in buck and when it will be in boost, right? Do you
Yes.
remember? You
Uh,
asked me the question.
yes, yes, yes. I asked the question.
Yeah. Then I told you to check with the voltage. So do you remember? Have you checked?
I think so. Yes.
Yes. So can you tell me from which voltage up to which voltage it is buck and up to which voltage it will be boost?
I didn't understand the question.
Okay. See, buck boost means what? It will be buck for some time and boost for some time, right?
Yes.
So I'm asking you up to what time it will be buck and up to what time it will be boost.
Depends on the switch, right?
Like see, output buck means what? It will step down,
Yeah, yeah, yeah.
clear, and boost means what? It will step up.
Yes.
Yeah. So I'm asking, like, up to which time, that means up to which voltage it will step up, and up to which voltage it will step down.
From the input voltage, because if we want a certain voltage, but the input voltage is more, we use the
Mhm.
buck mode so it can get it down to the voltage we want. And the same time, if the input voltage is low than what
Mhm.
we want in the output, we use the boost mode so we can step it up.
See, can you see my screen here?
Yeah.
Yeah. What I'm actually telling in buck boost. Okay.
Yes.
In buck boost, suppose I'm telling about initially buck.
Okay.
In buck, what is the relation of output voltage and input voltage? The relation between output voltage and input voltage V naught by Vi is D.
Yes. The
D is the duty cycle.
Yeah.
And in case of boost,
One
the
over
R
one minus
by
the
input is 1 upon 1 minus D.
Yes.
Now suppose I put D as 0.3. Okay.
Okay.
I put D as 0.3, and I need to check for buck and boost both. So for buck, if I check for 0.3, what will be the voltage?
The input?
The output voltage, V naught. V naught will be equal to 0.3 into Vi.
Yes.
And suppose I'm assuming um, Vi to be 10 volt. So what will be V naught?
7. No, 3.
3 volt. Yeah. This is for the buck.
Yes.
Now for the boost, I will take the same 3 volt, 10 volt and 0.3 duty cycle. What will be V naught? V naught will be equal to Vi by 1 minus D.
Yes.
It will be equal to 10 by 0.7.
Yes.
It will be equal to how much?
Uh,
Calculate.
it's gonna be 10 point, uh, I think
It will be
10 point something, I think.
it will be
Oh,
14.2.
okay.
Okay.
Yes.
Now see, in buck, what happened? The voltage is decreased
Yes.
from 10 volt to 3 volt. In boost, what will happen? It increase the voltage from 10 volt to 14.2.
Yes.
Now our concern is buck boost.
Yes.
For buck boost, the relation is V naught by Vi will be equal to minus D upon 1 minus D, right?
Yes.
So here in this case, suppose I take the Vi is same as 10 volt and D as 0.3.
Okay.
I'll calculate the V naught. What will be the V naught? Minus 0.3 into 10 divided by
1.
0.7.
Yes.
So it will be minus 3 upon 0.7,
Yes.
which will be equal to 4.28.
Okay.
So what can you see? The voltage is reduced or not?
Yes.
So it is operating in buck mode.
Yes.
Now you will ask me then when it will operate in boost mode. Okay.
If the wait,
I'll tell you. So now if we increase the duty cycle, Vi is same 10 volt. Okay.
okay.
And D will be 0.5.
Okay.
So now, if we calculate again the V naught, it will be minus 0.5 into 10 divided by 0.5.
Yes.
So this, if we cancel, it will be how much? 10 volt.
Yes.
The output is equal to the input voltage, right?
Yes.
Now we'll calculate what? We'll calculate for D equal to 0.6, where V naught will be equal to minus 0.6 into 10 divided
Yes.
by 0.4.
Yes.
That will be equal to minus 6 by 0.4 will be equal to, let me calculate. It will be equal to 15 volt. So it is operating in boost mode, because see, initial voltage was 10 volt and now the output we are getting is 15 volt at duty ratio of 0.6.
Yes.
Can you see?
Yes.
Yeah. So the reason where it changes from buck mode to boost mode is D equal to 0.5. See, if D equals to 0.5, we get the same, the input and the output voltage are same.
Yes.
So this is, you can say, as the reference voltage, reference duty cycle 0.5. So
Okay.
till you can say 0.4, it will operate in buck mode, and after 0.5, it will operate in boost mode.
Okay, nice.
So your doubt is clear?
Yes, yes.
Yeah, your professor might ask you these things. Okay.
Yes, of course. Yes.
These are very important thing.
Yes.
Okay, now let's move to the earlier. Okay.
Okay.
Okay. So a buck boost DC-DC converter operates in two major modes: buck mode, step down, and boost mode, step up.
Yes.
Right? As seen in the illustration, I think some figure is given in 2.1. Yeah, this is the figure is given. Okay.
Yeah.
There is also a transitional area that the converter functions as an electric buck boost. Okay. There is some area in between in which it will operate. Okay.
Okay.
The area is the, what I said, we calculated as D equals to 0.5, right?
Yes.
So that is considered as, you can say, the reference or kind of area. So before that, it will be buck, and after that, it will be boost.
Okay.
The buck functions, the buck function involves periodically turning off and turning on the switch. So you understood what is turning off, turning on?
Yeah, for the switch, yes.
Yeah, which is typically an integrated circuit or MOSFET, which are
Yeah.
MOSFET will operate. Okay.
Yeah.
Energy is stored in the capacitor. You can ask me any doubt in between. I'll just try to read and explain. Huh?
Okay.
Energy is stored in the capacitor once the power switch is turned on. So that we know that energy is storing in the capacitor of our either buck or boost, right?
Yeah.
So lower the voltage output.
The power switch is turned on. You mean it's
See,
closed, right?
if we see this circuit,
Yes.
okay, if the power switch is turned on, what will
So it's
happen?
closed.
This will
Then
be
it
closed.
will be stored in the capacitor.
It will move to the capacitor. The capacitor will start storing the energy.
Yes, yes, yes.
This is only it is telling. Okay.
Okay.
Energy stored in the capacitor is switched on. Lower the voltage output is the result of the inductor discharging. It stored power via a diode to the outlet while the switch that controls it is off. See, last class, do you remember I explained the use of diode, why diode is used?
Yes.
What it does, it discharges the inductor.
Yes.
See, it is written in this literature paper also. Okay.
Yeah.
Lower the output voltage, the result of inductor discharging via a diode. Correct?
Correct, yes.
When the supplied voltage is greater than the intended output voltage, buck mode is triggered. So when the buck mode is triggered, when the supply voltage is
Is
greater,
greater.
when Vi is more than V0.
Yes.
When the result needs to be decreased, this approach is appropriate. That means when we need lesser output voltage, then the buck mode we require.
Okay.
The button is once more intermittently turned on and off when in turbo mode. Okay.
The button.
Button means it basically includes the switch button only.
Oh,
Okay.
the switch.
Turn off, turn on based upon the duty cycle, the pulse. Okay.
Yeah.
The capacitor stores energy when the power button is turned on. When the button is turned on, the capacitor will store energy.
Yes.
The inductor stores energy when the switch is turned on. So inductor will store energy when it is?
The switch is turned on.
Yeah. Like, see, when it is turned on, both the inductor and the capacitor both will store in some energy, right?
Yes.
So that's what it's telling. Now, a higher output voltage is the result of the inductor discharging its energy to the output through an output capacitor and a diode when the switch is off. When the input voltage is less than the intended output voltage, boost mode is triggered. Now it is explaining actually about the boost mode. Okay.
Okay.
How you will get the higher output voltage. So that means it's just telling that when the switch will be off. Okay.
Mhm.
When the switch will be off, what will happen? The inductor, what is the energy will be stored in here?
Magnetic field.
Yeah,
Magnetic.
in terms of magnetic field. Okay. The energy will be stored in here, and that energy will be distributed through the capacitor and through the load
Yes.
because the switch will be off.
Yes.
So it is telling that in that case, the inductor discharging its energy to the output through an output capacitor and the diode, and the switch is off.
Oh.
Okay.
Yes.
When the input voltage is less than the intended boost trigger. When an application calls for a higher output voltage, this mode is used. So it depends. When we require higher output voltage, then we require the boost. Okay.
Yes.
Okay. Suppose in kind of, you can say, grid application. Okay. In kind of for applying to DC motor and all, we require this boost converter.
Yes.
A relatively constant output voltage is maintained by adjusting the switch duty cycle in the transitional region between the buck and the boost mode. So some kind of constant output voltage is maintained. Okay. Because in case of duty cycle D0.5, we have seen that the Vi is 10, the output is also 10.
Yes.
This indicates that during each switching period, there are cycles of energy release boost like buck like due to the switch being on and off for the portion of the time. That is, it's telling it will become on and off. Once it will act as boost and once it is buck. Okay.
Yes.
When the input voltage is not constant with the desired output voltage, the buck boost mode is triggered, necessitating flexibility in voltage regulation. So in case of certain applications, like I said you in the last class,
Yeah.
that in case of PC, we require the lower voltage, suppose
Yeah.
pen drive and some chips, then we require the buck.
Yes.
But in case of higher applications like DC motor, then water pump, then we require the boost.
Yes.
But there are certain applications like I said you the uh, photovoltaic application. Have you seen?
The one?
The PV, it is connected through buck boost to a application in which it is once time require it is requiring 40 volt, but the solar panel is when the sun is very high, it is giving 50 volt, and sometimes when it is cloudy, it is giving 30 volt.
Yes.
Do you remember that application?
Yes. Yes.
Yeah. For that, we require the buck boost. So once it will step down and once it will step up so that we get the desired 40 volt.
Okay.
Okay.
Yes.
So for that, we require the buck boost mode is triggered in that case. Okay.
Nice.
So there is one reference. Have you seen? Have you checked the reference?
Which one?
This one. This reference.
What's about it?
Alphas, okay.
Okay.
2009 adaptive fuzzy logic controller for DC-DC converters. Okay.
Yes.
So I have downloaded the reference. Okay. This one, 2009.
Yes.
I'll show you. Have you read any like research papers and all till
Yes.
now?
I have read the few. Yes.
You have read, right?
Yes.
Going to share everything. Is it visible?
Yeah. Yeah.
Yeah. This is the paper. Okay.
Okay.
This is the paper which is shown here. I'll just give you some idea. Okay. It's not require some detailed explanation right now. Okay.
Yes.
When it is required, we'll discuss. What it is saying? It is saying adaptive fuzzy logic controller for DC-DC converters.
Okay.
So what is fuzzy logic? Fuzzy logic is a type of controller and they have using adaptive type. Adaptive means you can change the gain. Okay.
Yes.
That is for your DC-DC converters, whatever you require, either buck boost or buck boost. Okay.
Okay.
So what is the abstract is saying? This paper introduces a complete design method to construct an adaptive fuzzy logic controller for DC-DC converter.
Yes.
In a conventional fuzzy logic controller, comma, knowledge on the system supplied by an expert is required for developing membership functions and control rules. That means in this fuzzy logic controller, while
Yes.
designing, you require some what called something called membership function, okay,
Okay.
and control rules. So
Yes.
this needs to be designed by an expert. Okay. So some designing proper methodology you have, if you know, then only you can design it. Okay. The proposed method do not require expert for making parameters and control rules. Instead, parameters and rules are generated using a model data file. Okay, which contains summary of input-output pairs. The fuzzy logic controller use Mamdani type. That means we have to use some kind of method for fuzzification, defuzzification. So it uses Mamdani type. Okay. The proposed converter is designed, controller is designed and verified by simulation.
Yes.
And then implemented for buck boost and buck boost converters.
Okay.
Right. So this is basically the work which is they have done, okay,
Yes.
which is mentioned in your literature. Fine.
Okay. Nice.
So that detailed, I don't think it is required right now, right?
Yeah. No. No.
Yeah. So now, yeah. So these are the three type of circuits. Okay, it's saying that illustration 2.1. This one figure 2.1.
Yes.
Yeah, this figure 2.1 is this 3 circuit. Okay,
Yes.
so you tell me this literature survey is uh, given to you by your professor.
No, it's
This
not given to me by the professor.
to read and
Uh,
explain it to him.
no, no, no. So what happened is the professor gave me the reference in the end,
Okay,
and he told me to write approximately 800 to 1,000 word
okay,
from this reference. So I read the reference, I take some some information,
yeah.
then I put it in the lecture review and say I took it from this reference.
Mm-hmm.
But that's not hard. I did it. This one is the one I did. But
Mm-hmm.
when I read it, I don't fully understand it. So when the professor asked me, I
Yeah, yeah.
can give him half answer. He want me to give him a full answer because this is my final year project. So he
Uh-huh.
told me all of these you wrote are
Uh-huh.
very good. You were gonna use it in your project, but
Uh-huh.
now go and basically study them
Okay,
and
okay,
come back to me. So I have in a few days, I'm gonna
Mm-hmm.
take a meeting. I need to explain everything to him. So that's why I was a little bit confused when I read everything.
Yeah,
So
yeah.
but the first one you have read, I know everything about now, and we can
Mm-hmm.
continue now.
Yeah.
So yeah, I understand it.
Okay. So from the earlier reference paper of Elmas, okay,
Yes,
these are the 3 circuits and these are the values which they have used for the simulation. What is the simulation they have used? Fuzzy logic controller. Okay.
yes,
This is for bug, this is for boost, this is for bug boost.
yes,
Next line, Rodriguez, Vez, and Toffoli. This is also one paper.
yes,
Okay. It explains, this is also you can say here if you want. Rodriguez, where is Rodriguez? Yeah, the second last, this one
yes,
explains about the passive snubber. So I think you have a doubt what is snubber.
yes.
So that's why I have written it here. A passive snubber is a circuit, okay,
Yes.
used in power electronics to control voltage and current transients in a switching device such
Okay.
as a transistor or a diode. So in case of our circuit, this is our circuit, suppose. What are the switching element? The switching element is either this MOSFET or this diode.
Correct. Yes.
So in this switching element, in order to control the current flowing and the voltage,
Yes.
a passive snubber circuit is designed.
Okay.
Now, what is the term snubber? The term snubber refers to a circuit designed to dampen or suppress unwanted oscillations or spikes in a system.
Okay.
There might be, suppose we are giving a input voltage, we might get a output, but that output might have lot of fluctuations, lot of noise. We might not get the desired output. It may be some kind of output voltage which is not required by us.
Okay.
So in order to dampen or suppress, remove it, snubber is used.
Nice.
In power electronics, passive snubbers are commonly employed to mitigate the effects of switching events, which can lead to voltage spikes and ringing. These events occur when a semiconductor device, such as a transistor, turns on and off causing abrupt changes in voltage and current. So same, it is explaining that when the switch is turned and on and off, there might be sudden change in the voltage or current.
Yes,
Okay.
yes,
So in that case, your circuit might damage.
yes.
In order to reduce that spike, we use the passive snubber.
Okay,
The passive snubber helps reduce the stress on the components and improve the overall system performance. Right?
okay, yes.
Now you might ask, what is the snubber then? The snubber is nothing but simply the components which include resistor, capacitor, and diode. Okay.
Okay, so when someone says number, it means a combination of resistor, capacitor, and diode in a circuit.
Yeah. No, it's not like that. All the three might be there.
Oh,
Sometimes there might be only resistor. Sometimes there might be resistor and capacitor. Sometimes resistor, capacitor, diode, both. It
okay,
depends.
okay,
It is upon your requirement.
okay, nice.
The next line is, it offered an enhanced converter design process and examines the impact of the snubber circuit while weighing the trade-offs between losses and voltage stresses. What he says, it offered an enhanced computer design. That means this paper will show a design of the converter
Okay,
and it will examine what will the snubber circuit will do when what will be the effect without the snubber circuit and with the snubber circuit.
okay,
They will do a comparison.
yes,
The theoretical presumptions were also supported by experimental results. They have also done some experiment to verify that.
okay,
The alternative method for calculating the static gain in a DC-DC buck-boost converter that was presented in this paper is based on the inductor charging and discharging times, which was connected to the rated power and voltage gain specified in the design specification. So it is saying that we have calculated a method to determine the gain, right? V naught by V equal to minus D upon 1 minus D.
yes,
So that is one gain. So they are saying that in this paper, they have also shown one alternative method. That means another method
okay,
based on the inductor's charging and discharging times. That means how the inductor is charging, discharging,
okay,
which is connected to the rated power. That means the supply and
yes,
is gain specified in the design specification. So if we check this paper, okay,
yeah,
then we'll get to know what is the alternative method. That's what
okay,
only it's saying, right?
yes,
Okay. Next line, the analysis revealed the static gain in all the three operation mode. So these three are the operation mode:
yes,
CCM, DCM, CRM. Okay. Now,
okay,
this mode mainly whenever you will study the power electronics, okay,
okay,
you require only these two modes, CCM, DCM.
okay,
Actually, when we'll take next class, like after this, your discussion class is over, when we'll take next class,
mm-hmm.
I'll explain you what is CCM and DCM in details. Okay.
Okay, nice,
Yeah. So here just I want to say you, CCM is called a continuous conduction mode.
okay,
DCM is called a discontinuous conduction mode. And CRM is called critical conduction mode.
okay,
Okay, just you need to remember right now these three things. Okay,
okay, okay, no problem.
yeah, these three could be calculated using the same expression. Furthermore, the converter analysis may be predicated on variations in the output voltage or the load. So based on the variation, suppose we do not have like the constant output voltage, right? Our
Yeah, yeah.
output voltage may vary based on load. Load may change.
Yes.
So those analysis is also done in this paper.
Okay, nice.
The specs of the buck boost converter used in the study are shown in the table. So there is a table. Yeah, this is a table. In this
Okay.
table, they have given all the parameters which they are using in their paper.
Yes.
Okay.
Okay.
Okay. I can even show you this paper Rodriguez Vez. Okay.
Okay. Okay. Nice.
Mm. Yeah. Can you see?
Yes.
Mm. Detailed design procedure of a DC-DC buck boost converter employing a passive snubber. This is the paper of Rodriguez. So what it says, this paper presents an optimized design procedure for a DC-DC buck boost converter associated with a dissipative snubber. That means it is using a snubber circuit.
Yes.
Based on the snubber circuit, they have designed a optimized design. Initially, the static gain of the converter is determined from the charging and discharging times of the inductor in an approach that is valid for any conduction mode and does not depend on load conditions. So initially, what they have said, the gain is determined from the charging and discharging, what we have explained earlier. You understood?
Yeah, yeah.
The influence of the snubber circuit is also analyzed considering a trade-off between maximum voltage stress and this thing. So this is the paper in which this is the buck boost converter design. And later on, I think they are using stages considering the operation in DCM, that is the discontinuous conduction mode they have used. So first stage, second stage, third stage, how the current will flow, okay, on and off condition they have considered. This is like the detailed paper. So right now we do not require.
Yeah.
See, these are the experimental results, and these are the table value that you have taken from this paper. These are the results they have got while doing the experiment. I think they have used microcontroller they have used for the getting the output results. And this is the conclusion. Okay.
Okay.
This is a conference paper actually
Uh-huh.
published in 2017. Okay.
Yes, yes, it is.
Now let's move to our discussion. So next part is explained by Abhishek. Okay, in 2020, what he did, he created and examined a DC-DC buck converter and boost converter to change the input voltage and duty cycle and reach high efficiency. So
Yes.
what is his work? His work is to create and examine buck and boost converter to change the input voltage and duty cycle. That means he is changing the circuit. Okay.
Okay.
He's changing the circuit to reach high efficiency.
Okay. Yes, yes.
Some kind of change he has done. Okay, let me also, it will be clear, I think. This paper. Okay. Design and analysis of a DC-DC buck converter and boost converter to achieve high efficiency by altering duty cycle and input voltage. This paper explains DC-DC buck converter and boost converter, which cites the dependency of duty cycle input voltage on output voltage. It consists of elements like MOSFET, transistor, inductor resistors, and ng-spice simulation has been conducted to analyze the efficiency of the DC-DC buck converter and boost converter. The results show the efficiency. So what it shows, it changes the circuit and analyzes the efficiency. Okay,
Yes.
but only that's the work of this. And he has done the simulation in ng-spice.
Yes.
He just tested the simulation and he has just plotted it, the results. This is kind of, I think, not that tough, simple work he has done.
Okay.
Okay. So let's move to our next part. Okay. So the simulations outcome demonstrated that when input voltage and duty cycle were raised, the DC-DC buck and boost converter rose, efficiency rose. So what he has analyzed that when the input voltage is increased and the duty cycle also increase, then the efficiency increase as well. Okay, that he has checked. That is his work mainly.
Okay. Yes. Yes.
Okay, that means he wants to test the efficiency, right? So what he got the result that when we increase the input voltage and duty cycle, then the efficiency is also increase in the circuit.
Yes.
That's what he has done. So you can see this is the efficiency graph he has got. When the
Yes.
duty, see, this is the duty cycle in the x-axis and the y-axis is the efficiency.
Yes.
So when the duty cycle increases, the efficiency also increases,
Okay. Yes.
right? Same in
Okay.
case of the efficiency graph of the input voltage. If the input voltage will increase, the efficiency will also increase. That graph is not shown here, but that graph is also the similar manner. There is not very much difficult. Okay.
Which graph?
See, there it will be two, right? When the input voltage and duty cycle, there are two parameters, right?
Yes.
When the input voltage and duty cycle were increased, the efficiency will increase.
Yes.
So this is the graph of duty cycle and efficiency.
Yes.
There will also be a graph of input voltage and efficiency in the same manner.
Okay. Do
That is
you
what
think I need to put it in here?
you need to.
Is it better to put the figure for that one as well?
Uh, just wait. I'll check the paper. Okay.
Okay.
Let me check if it is mentioned there in details. cycle. That is increases the data cycle efficiency increases. Okay. In this case, they have used the variation.
Okay.
They have used the variation of this graph is you have shown the duty cycle versus efficiency, and they have used the graph of duty cycle and voltage gain. That when voltage duty cycle increases, the voltage gain increases. So I don't think you require that is okay.
Okay, nice.
Yeah. So we continue. So in the next paper, RD et al. Created, examined, and put into practice a buck boost DC-DC converter based on the cuck converter, resolving a few KY converter implementation issues. So what he did, he put a buck boost type of converter, okay,
Okay.
based on the cuck converter. What is cuck converter? Or you can say Chuk converter. This converter is a
Uh-huh.
higher order converter,
Higher what?
like higher order. Like see, in case of uh, buck boost, okay,
Okay.
we have one inductor, one capacitor, one diode, one MOSFET, right?
Yes.
In case of this Chuck converter or Cuck converter, this one,
Yeah.
you will find three inductor, two capacitor, like that. The order will increase.
Okay.
It will have more energy storing element because inductor and capacitor are considered as energy storing element. Okay.
Okay.
So you will have more energy storing element. Right.
Right, right.
Yeah. The proposed converter aims to increase the operational region of the continuous conduction mode and have a higher voltage gain. See, since the order is increased, so this will have high voltage. Because what we know? We know in case of boost converter, okay?
Okay.
In case of boost converter, what is the relation? V naught by Vi equal to 1 by 1 minus D. And suppose if we give a duty ratio of 0.3 and Vi
Yes.
of, we'll get an output of 14.2, right?
Yes.
In case of this, in case of this Cuck converter,
Okay.
in case of Cuck, if suppose the duty ratio is same 0.3 and Vi is 10 volt, the V naught maybe you will get it as 30 volt. It will
So
increase more. Because in case of boost, how much we are getting? 14.2. This one, see. We get 14.2 or not?
yeah, yes, yes.
In case of boost, we are getting as 14.2, na, while
Yes.
solving. But in case of Cuck converter, we'll get it at 30 volts, suppose. We'll get more.
How?
That we have to design and see. I am just telling you what the paper is telling. I am not read the paper, right? It will take again some time.
Yes.
Do you understood?
Yes.
What I'm
Yes.
saying, what is written in this paper? See, the proposed converter aims to increase the operational region of the continuous conduction mode and have a higher voltage gain in step-up mode. That means what? Whatever voltage you are getting in boost, you will get more high voltage here.
Okay.
See, this thing, just what is written, I am telling you, okay?
Okay.
If you need more explanation, then you have to study this Cuck converter. If you want, I can explain you, but it will take again time, na?
How long will it take?
Converter means this is one converter, na? So we have to design and we have to see everything. Basically, we need the relation between. I think if you want tomorrow, we can see that.
Because I don't think we cannot finish everything today. So if we study this tomorrow, we will not we will need another class to finish this file, right?
No, see this thing. Not much today. Already timing is over, but I can finish it tomorrow. Do
Yeah,
not worry.
nice.
I will
Okay, so
finish it tomorrow.
what will happen? We will finish it tomorrow.
Yeah, I will finish it tomorrow.
Okay, then we will take class so you can study me about the CAC converter.
So tomorrow you want me to explain Cuck converter?
No, tomorrow I wanted to finish the file.
Okay, okay,
After we take another class
okay.
for this one.
Yes, no problem.
Okay, thank
Okay,
you.
okay. So we'll end the class today.
Yeah, sure.
Okay, thank you.
Tomorrow when can you give me class?
Tomorrow, same time. You are okay?
Tomorrow same time.
Or you want some early before?
Uh, just 1 second. Tomorrow same time. Okay.
Huh?
Okay, no problem.
Same time?
Yes,
That means 3:30.
yes.
Okay, okay,
Okay.
okay,
Thank you.
okay. Thank you.
See you tomorrow. Bye.
Yeah, bye.